Hi everyone, so I'm just going to go through the first 5 questions, the short questions from the Oxford Mat. I'll get through the next 5 as well at some point this evening, so I'll try and post up another video for the last 5 questions tomorrow. I know somebody mentioned, Oxford mentioned in the comments he was looking for G. That is that is quite a nasty question as well, it has to be said. But yeah, let's go through it. Okay, so what's this first one about? So modulus question. I know, I think when I just glanced at the mark scheme anyway, checking my answers, I think they take the logical approach to solving this, which is a perfectly reasonable approach where you consider cases of when x is greater than 0 and when x is less than 0. I'm going to draw the graph just to show there is another way of looking at it, and I think this way is probably slightly quicker. If you turn this equation very quickly into x mod x equals 3 mod x minus 1, what we could do is try and sketch the graphs of y equals x mod x, which might scare you, but we'll talk about why it's not too scary in a second, and y equals 3 mod x minus 1. Now it's good to get to know how to handle these kinds of situations. With this kind of thing, I think, well, now we can just take critical values and think, well, when x is less than or equal to 0, yeah, you're going to have like a minus 5 in there, and you're going to immediately make it positive, if you see what I mean. And so you want to times that by minus x. So you want to consider y equals minus x squared there. I hope you can see what I mean there. What I'm saying is basically when x is less than or equal to 0, we might as well pretend this is minus x, because it is. Not pretend, we might as well take it to be minus x, provided x is less than or equal x is less than or equal to 0. So the y equals x squared graph, well, the y equals x mod x graph on this side is just going to look like y equals minus x squared. Whereas when x is greater than or equal to 0, because you can then just leave x as x, because mod x does nothing to it, you can just look at the graph of y equals x squared. So that's just going to go up like that, yeah? This graph isn't difficult to draw because it's just the mod x graph stretched by a factor of 3 in the y direction, then moved down 1. Clearly, when x is 0, y is going to be equal to minus 1. So it's just going to be a v-shaped graph like this, yeah? The one thing you might worry about is whether this misses the quadratic on this side, or whether it hits it twice, or whether it's tangential to it. I suppose there's 3 possibilities. Okay, I'm going to show you why this is actually what's going on. You could easily just very quickly take a value like x is 1, and you work out on this value y has got to be 2, yeah? But on the curve, when x is 1, y is 1, because you're dealing with y equals x squared. And so, that basically is there on the line where as the curve should be underneath it, if you see what I mean. That's how I know the curve's going to go underneath the line at that point. Just take 2 values, in between, and then you're there. Anyway, now I can just look at it and say 3 solutions. Boom. Okay, B. I've drawn some circles out to help me here. This one's a funny little one, isn't it? Like, you have to read it carefully. You're like, okay, what's going on exactly here? But once you've read it carefully, you realise, okay, this is going to be C1, C2, and C3. Yeah, they've told me that is it a tangent crosses this circle, so I'll just draw a very straight line. Yeah, and we know that the distance initially is separated by C1 has C1 has a radius of 1. Yeah. And where am I getting 1 here for? Because this is a distance of 2. Every single time, doesn't matter how big you are, that must always be a distance of 2. That was one, when I first read it, I kind of got it a bit messed up because I started drawing it and I started looking for, I thought it was just the initial one which had a distance of 2. And we kind of went out like in straight lines like that. But no, every single one of them is going to have a distance of 2 when you draw the tangent. So the circles aren't going to be evenly spaced like this, actually. But anyway. What we can do now, obviously, is work out the radius of C2 using Pythagoras. We got root 2 there, yeah? Now, okay, what happens on the next one when we draw it up here? Well, once again, we've got a tangent, yeah? I want to find the radius. Well, what's going to happen this time is this is now going to have root 2 up there. So let's draw that, because that's the radius. So that's root 2, yeah? And this is still a distance of 2, because each time Cn and Cn plus 1 at the 2 points, they're always separated by a distance of 2. So this is still 1. And now we want to find the radius of C3. And we're going to do root 2 squared plus 1 squared, equals the radius. And so let's have a look at the sequence we're building up here. Like C1 has a radius of 1. C2 has a radius of root 2. C3 has a radius of that squared plus that squared, square rooted, that's root 3. I'm sure you can see now C4 is going to be root 4. In other words, if we put a root on this one, the pattern's nice, and therefore C 100 is going to be just root 100, and so the answer is 10. Okay. Hopefully I've got these answers right. I'm pretty sure I have. Okay, right, brilliant. This one. What we got here? We've got a circle. Oh yeah, and we've got this. Okay, so if we immediately try and make it into a typical format for a circle, complete the square, in other words, on this bit, and complete the square on that bit. So y minus 2 all squared, and then we're going to have minus 4 plus 8, which is plus 4, and that equals k cubed minus k. And so we've got x minus 2k all squared plus y minus 2 all squared, and it equals this cubic. We get k cubed plus 4k squared minus k and minus 4. Yeah. Now, immediately I think I'm glad they wrote one down which really obviously factorizes, because always check with factor theorem as soon as you see a cubic. Are there some easy factors here? 1 plus 4 is 5, minus 1 minus 4 is 0, i.e. k minus 1 is a factor. I'm thinking that straight away when I see that cubic. Now, why would I want to factorize this? Well, because I want it to be greater than 0. Yeah, because that's the only way I'm not going to get a circle if the radius is negative. So I require, if you like, obviously you don't have to worry about smart notation actually on these questions, do you? Why am I changing the sign? Hang on. K cubed plus 4k squared minus k minus 4. Well, that's got to be greater than or equal to, greater than, 0. Yeah? Okay, so let's factorize it quite casually. I must admit, I quite like this way of factorising, and basically by inspection, we need a k squared to make the k cubed. That's going to give us a minus k squared, so we need 5 more k squared, so that must be 5k to give me 5 more k squareds there. That's going to give me a minus 5k, but I need just a minus k, so I need a plus 4. That will give me 4 extra k's to make that a minus k. That gives me a minus 4 in the end, so it's done, and then that gives you k plus 1, k plus 4 is greater than 0. So now, standard approach here would just be to consider like the cubic, y equals k cubed, k minus 1. Just draw this as a cubic. It's obvious what I'm doing, I hope. Call out y, then this is y equals the function of k. Okay, right, let's tidy that up a bit. Just draw the cubic. It's going to go through minus 4, minus 1, and 1. We want it to be bigger than 0, and so there, between minus 4 and minus 1, or there, 1. So it's minus 4 to minus 1, or k is 1. B. Okay, D. Sequence. Yeah, this one's like a number one. I quite liked it actually. It's kind of weird. I felt quite intimidated at first. All I thought was, try and work out A1, I suppose. And I'm thinking I've got 8 times 3 to the 4, which isn't very nice. But there we go. And let's write that in powers of 2 and 3, because definitely when you're doing arithmetic it's always better to work in the prime products, like it really is, it's easier. Okay, so A2, what's happening with A2? Well, this is like a recurrence relation, so we've got 2 to the 3 times 3 to the 4, but we're putting that to the power of 4 and then we're timesing it by 8, which is obviously 2 cubed. Now that's going to be 2 to the 12 plus the 2 cubed here, 2 to the 15, plus the powers, and then 3 to the 4 to the 4 is 3 to the 16, so we got 2 to the 15, 3 to the 16. That's interesting because that's one less than that one, that's one less than that one. Now if you go to A3, if you're brave enough to go to A3, you get the pattern because you've got 2 to the 15 times 3 to the 16 to the power of 4. I'm sure you can see what's going to happen here. We've got 2 to the 3 times 60, 2 to the 3 times 2 to the 60 times 3 to the 64. Add the power on, you got 2 to the 63 times 3 to the 64. When I got that far, I figured, I can see where this pattern's coming from as well. It would be interesting to try and prove it algebraically, come up with the general result. But when I looked at this, I thought, okay, so what am I doing for A10? Yeah, let's try and figure it out. Basically, this is always, these are clearly related to powers of, multiples of powers of 4. I'm looking at the 3 here, 4, 16, 64. That's like a geometric sequence, isn't it? Yeah. So let's just figure out the power on a geometric sequence. Let's just look at the power on 3. Yeah. For A1, it's 4. For A2, it's 16. For A3, it's 64. So we can easily work out now what it's going to be. If you like, you can just use that formula, can't you? UN equals AR to the M minus 1, I suppose. So 4 times by 4 to the M minus 1. And so U10 is going to be 4 times 4 to the power of 9, yeah? Which is going to be 2 squared times by 2 to the power of 18, which is 2 to the power of 20, yeah? Okay, great. We've got that as our power of 3. So we know that for A10, it's definitely going to be times by 3 to the power of 2 to the power of 20, yeah? Now remember that this one was always 1 less than that. That's supposed to say 63. That looks like 60. Let me smarten that up. Yeah? Look at this, that's always 1 less than that. It's always 1 less than that. It's always 1 less than that. So for this one, you're going to have 2 to the power of 20 take away 1. And at that point, I realised, well, that would be much nicer if we didn't have that take away 1 there. And that take away 1 is just a power of 2, isn't it? It's like dividing by 2 to the power of 1. And so what we can do is just write this as 2 to the power of 2 to the power of 20 over 2 times by 3 times, 3 to the power of 2 to the power of 20. A lot of powers in here. We can then add the powers. Yeah. Combine the 2 and the 3 because they've got the same power on it. And so this is the same as 6 to the power of 2 to the power of 20 over 2. Yeah. What result I'm using there is a to the x times b to the x is ab to the x, obviously. That's the result I'm using there. Sometimes it's not clear to people that, but yeah, I'm not adding any powers there, sorry, on that last step. I'm just turning the 2 times 3 into a 6. That's what I'm doing. So anyway, the answer's E. Part E. Okay, this one, I was tempted to do that and that on a binomial expansion. I haven't done that way yet. What I actually did, just because I thought powers of 4, that's not that bad. Let's just write it firstly as x squared plus x plus 1 over x to the power of 4. And then I thought, well, I'll expand the top now, and I'll just do it the long way, really, I thought. If I'm doing x squared plus 1 squared, x squared plus x plus 1, squared. If you want to do it super quick, you just get the pattern, I think, in a grid. I really do. I can just see what's going on there. That's going to give me x to the 4. I'm going to get an x cubed here and x cubed here, so 2x cubed. Yeah. And you could use a binomial approach by this and that. I'm just kind of regretting this now. And then an x squared and then an x squared and an x squared. Lots of ways you get x squares here. 3x squared. Sorry about my terrible handwriting here. It's getting worse. Cool, and then we get x and x and we get 1. Bad news though, we got to square that because I've got to square it and square it again, and this is over x to the 4. Now at this point I don't really think I did any squaring at all, because really I'm only interested in x, in the term independent of x. Now what does that mean? That means the term hasn't got anything to do with x. It's independent of x. Only interested in so I want x to the power of 4 terms on top, yeah, because they will cancel with the x to the power of 4 on the bottom. So let's just see how I'm going to get that. Well, it's going to be really similar to last time. How are you going to get an x squared? Well, you're going to have that times by that twice. So that's 2 times 2x cubed times 2x. You're going to get this term times by itself once. So plus a 3x squared. Yeah, think of the grid I've just drawn out. Draw it out yourself if you want to do it with but you just have 5 terms along the top and down the side, and that just 25 terms in a grid, it's a bit much, so that's why I'm just doing it by inspection and just looking at the x to the 4. How else would you get an x to the 4? You could do the other way around of x to the 4 times by 1 times by 2. Oh, and this is supposed to be 3x squared plus 3x squared times 3x squared, so that's actually 9x squared. Look at that, I'm writing it down wrong. Crazy, because it's 9x to the 4, sorry. We're timesing that by itself, yeah? We're timesing that by itself. We're going to do that times that, and we're going to add it twice, and then we're going to do 3x squared times 3x squared at some point, and that's going to give us 9x to the 4, and then we're going to do x to the 4 times 1, and 1 times x to the 4, and that's why we're going to get plus 2x to the 4 in the end. Over x to the 4, what does that come to? We've got 8 plus 9 is 17, 18, 19. And so I think the answer is C. Okay, thanks for listening. I will do, like I say, F to J very soon, very soon. But let me work through it first. I did look at G though. I appreciate what you mentioned about that. It is quite a tricky question, but I'd love to have a go at it. Okay, all the best. Bye bye.